Okay, so today we're going to dive into a little bit of a higher level concept, which is the idea of chemical equilibrium, and the idea of balancing forward and backwards reactions and how they apply to acids and bases. So again, we're not going to do equilibrium as a full thing this year, so I wanted to make sure we got a little bit of an idea in terms of what this is. And the concept of a slinky on a treadmill or a slinky on an escalator is a great picture that you're going to use to get your head around the idea of what equilibrium is. So talk about forward and reverse reactions. Most of the reactions that we have seen have just gone forward. We put two chemicals together, they form a precipitate, boom, it's done. The bigger field of chemistry, however, has a lot of reactions where there's a little bit of give and take. There's kind of a forward reaction and there's a little bit of reverse reaction. So this is that idea of a slinky and an escalator. What happens if you put a slinky going down? Well, if the rate that the slinky is going down is faster than the rate of the escalator is going up, then the overall movement of the slinky is going to be down that escalator, right? And it's going to be what we consider a forward reaction. If we have the opposite, let's say that slinky is going down, but the escalator is moving up really fast, then it's, in a sense, that slinky is moving backwards. It's kind of like the reverse reaction wins. And in the, of course, awesome situation that we have the forward rate exactly equal to the reverse rate, that the slinky is going down at the exact same rate that the escalator is going up, then we have a type of equilibrium, right? There's a balance point there where no matter how long that slinky stays on that escalator or that treadmill, it's going to be continuing over and over and over again. And this is that concept of equilibrium, and it actually does apply to our understanding of how acids and bases are classified. So, in terms of these two things, we got to think about forward and reverse reactions, and it's kind of tough, but we got to think about it in terms of products and reactants. So if we know which of the two reactions is faster, the forward or the reverse, we can get an idea of, at the end, are we going to end up with a lot of product being made, or are we going to end up with reactants left over, which is kind of a weird thing to think about. If a reaction is going forward, and that we've got more forward than backwards, then overall our net movement is going to be forward, and we're going to have products built up. Maybe not as fast as some of the ones that we've seen in lab, where they're just like 100% solid, done kind of things. But that would be a forward reaction dominating, more product is being produced. In these kind of weird cases where the reverse reaction is actually faster than the forward reaction that we want, we end up with only a little bit of product made, but a lot of that product tends to go backwards into reactants, and we end up with a lot more reactant left over at the end of the situation than we would expect. We can represent this sort of balance with these funky little mathematical equations called equilibrium expressions. You're not going to be tested on this in this chapter, but I want you to have some idea what this is. These little equilibrium expressions kind of look like this, where we talk about concentrations, and this little square brackets mean concentrations. So this would be the concentrations of our products on the top, and the concentrations of our reactants would be on the bottom, of basically a fraction. And so if you think about it, if we've got a lot of products, then our numbers on the top are going to be pretty big, and the amount of reactants left at the end are going to be pretty small. And so this is going to be a big number. Our forward reaction is going to predominate, and we're going to get a value greater than 1. And that value would mean that, hey, the products are favored, that reaction is overall moving forward. On the other hand, if we have one of these weird cases where the reverse reaction is winning, then we're not going to have a lot of product. This value is going to be pretty small. And we're going to have a more product or more reactant at the beginning, at the end when we're done, than we did at the beginning, which seems kind of backwards. How's that possible? But trust me, it can work. In this case, we end up with a fraction. This is going to be a small number over a bigger number, and we get a KEQ less than 1. It's not negative. It's between 0 and 1, a fraction, a decimal place. And that means that the reverse reaction is actually predominating. Again, you're not going to get that idea. I just want you to understand that these equilibrium expressions kind of give you the overall idea. Is the slinky moving down like it should? That would be a forward, a KEQ greater than 1. Or is that slinky getting pulled back? And that would be a KEQ less than equal to 1. And that's that idea of equilibrium, that overall balance between the forward and reverse, and how we can mathematically represent it with something called an equilibrium expression, or a KEQ, is what those things are called. So this is how it applies to our ideas of acids. That we learned in the last video about strong and weak acids, that strong acids let go of their hydrogens, and weak acids tend to hang on their hydrogens. It's not quite that simple. It's actually in reference to equilibrium. So in the case what we've got here is that strong acids, that's very much a forward reaction, that those hydrogens let go, get away from their negative anions, and really the reverse doesn't happen very much. So the reverse would be these guys coming together to make an acid. It doesn't happen very often, so this tends to be a pretty much a forward reaction winning, so we get almost 100% ionization, lots of hydrogens being released. In weak acids, though, this is not the case. even though some of these hydrogens get released, what we find is that there's a much stronger attraction between hydrogen and the negative ions, so it tends to want to go this way. It tends to create more of this reactant than it does to create the product. And so we kind of get a reverse reaction predominating. More of this reactant stays as reactant. Anything that falls apart tends to build right back up, and therefore we get very little dissociation, and we call those weak acids. Same thing could be true with bases, the same basic idea. But again, strong and weak acids has to do with the concept of equilibrium, whether that forward reaction, dissociation, or whether the reverse reaction, conjugation, actually takes precedence. So when we're talking about equilibrium expressions for this is kind of what they look like. Pretty straightforward. It's just like what we saw in that earlier bit. We've got the reactants on top and the product on the bottom. Sorry, I think I said that totally backwards. Products on the top, reactants on the bottom, edit, delete, rewind. And if we think about this for strong acids, our products are going to be in much higher concentrations, and all of this reactant will basically have fallen apart, so this number becomes very small on the bottom, big numbers on the top, and our KEQs are pretty high. They're greater than 1. For weak acids, which are the opposite, we tend to get a lot more of this bottom part and a lot less of the top part. We don't get many ions present, and the KEQs for weak acids are less than 1. Again, greater than 0, can't be a negative number, but you get fractions, 0.3, 0.5, something like that. So what's weird is now we have to actually apply this concept to water. Water itself dissociates. Water itself turns into ions all by itself. It's kind of a crazy thing that it does. It doesn't do it very often. It doesn't do it very much. Very small percentage of the time that we get some of the water molecules will spontaneously give up a hydrogen, and other water molecules will spontaneously receive that hydrogen. And again, we've got water molecules. Here's our hydronium ion and our hydroxide ions. We talked about acids and bases and conjugate acids and bases in the last unit. This is kind of bizarre to think about water doing this. So water's acting like an acid and a base at the same time. Some water molecules are donating hydrogens, some water molecules are receiving hydrogens. This is the definition of an amphoteric substance, and you need to know this word. Amphoteric substances are chemicals that can act either as proton donors or proton receivers, depending on the circumstances, kind of what they're around. And water is by far the most common one. There's some other ones. Here's a couple examples of other ones. I'm not going to test you on these, but just so you can see, you may want to hit pause and really kind of take a look at these. It's good practice of that acid-base, conjugate-base stuff we were doing in the last unit, that these other types of ions, these ions that include hydrogens, this one's the most famous one called bicarbonate, and that's one that you know of, that sometimes it can accept a hydrogen and sometimes it can release an additional hydrogen. But these are amphoteric substances, substances that can act like either an acid or a base, depending on the circumstances. So, in terms of this, we can now express this as an equilibrium expression. It's a type of a KEQ. We could say that, well, the KEQ of this, here's our reactants at the bottom is just plain water. Here's our products, hydrogen and hydroxide ions, or this would be a hydronium, I know, if you want to be technical. So when we write this equation out, notice how they've dropped the water in this? Well, the reason for that is kind of a little picky thing. Don't worry about it too much. The concentration of water is 1. I know it sounds kind of funny, but water is always 1 mole per liter. It's kind of a definition of what water is. It's as concentrated as you can't get more concentrated than water. So I know it's kind of a weird thing, but it's left out. And that's why they change it from a KEQ to something called a KW. This is the ion product constant of water. So we know that for water, that it's just the product of the hydrogen ion and the hydroxide ions. It turns out that this is a constant. It does it at a very low rate, 10 to the minus 7th molarity, 0.0000001. Of the time it does that. It's a pretty small quantity, and that's how much hydrogen and hydroxide that you get. So the ion product constant for water is 1 times 10 to the minus 14th. It's kind of a crazy value, but it's something that we're going to use. And yes, you need to know this value, 1 times 10 to the minus 14th, and you need to know that these two 10 to the minus 7th is what happens in neutral kind of circumstances. So this KW equation, it's in this green box. You need to know this for the test, and you need to be able to use it. So I'll show you how to use it in the next slide. So, in terms of doing this, we can start to identify solutions as being acidic or basic, because if we mix them with water, we're going to change the amount of hydrogen or hydroxide that's present. We're going to shift that balance point, right? It's like turning the slinky up faster or turning the escalator up faster, simply by nudging it one way or the other. So, it turns out that the product, the multiplication product of the two will always be the same. KW is 1 times 10 to the minus 14th. That value never changes. But the balance of forward and reverse, the balance of hydrogen and hydroxide, shifts just a little bit. And we can say that we can define acidic solutions now as ones that have a greater concentration of hydrogen than hydroxide. Same thing with bases. We can define bases now as solutions that have more hydroxide than hydrogen. That's kind of what we've learned with our acid-base definitions in the last one. But still, in a neutral solution, we know that the two concentrations have to be equal, and they're equal to 1 times 10 to the minus 7th. So let's take a look at how this works. So let's say that you've got a solution that's got a hydrogen ion concentration, H+, of 3.4 times 10 to the minus 4 molarity. So what is the hydroxide ion concentration? You're going to use Kw to find that. And then the last part is that solution acidic, basic, or neutral? And that's kind of that last slide that we just did. So take a second and pause it. See if you can plug this value into the Kw equation and see if you can figure out what the hydroxide ion concentration is. Hit pause, work it out, then come on back. All right, so did you actually hit pause? I hope you did. So here's our Kw expression right here. That's that formula that you need to know for the test. Here's where the numbers plugged in. So 1 times 10 to the minus 14th is Kw. That is the hydrogen ion concentration. This is from the problem. Times the hydroxide ion concentration. That's our unknown. That's what we're trying to find. When you rearrange this, you get a hydroxide concentration of 2.9 times 10 to the minus 11th. That's a really small number. 10 zeros and a 2 and a 9. It's a pretty small value. So we take a look at these now. This is the second half. Is it acidic, basic, or neutral? Well, we have to know the ratio. Which one's bigger or which one's less? If they're equal, then we know it's neutral. If hydrogen's greater, then it's acidic. If hydroxide's greater, then it's basic. So we take a look at these two values. We've got 3.4 times 10 to the minus 4th and 2.9 times 10 to the minus 11th. That hydrogen ion concentration is quite a bit bigger than the hydroxide ion. Therefore, this would be an acidic solution, and fairly acidic at that. So there you go. Here's your main ideas from today's bit about equilibrium a little bit and about acid-base concentration and amphoteric substances. So number one, understanding there's an idea of a forward and a reverse reaction, and that these relate to how much reactants versus products are left after a reaction has continued for a little while. Strong and weak acids are actually definitely related to this idea of reaction rates. That strong acids, the forward reaction predominates and all those hydrogen ions are released. In weak acids, the reverse reaction predominates and the hydrogen ions are sort of captured or held onto in their sort of full molecular form. Equilibrium expressions are simply a mathematical way to express that if we have forward reactions are high, are the big ones, the normal ones like we're used to, then you're going to have a KEQ greater than 1, sometimes lots greater than 1. If a reverse reaction is predominating, like in a weak acid, we're going to get KEQs that are between 0 and 1, a decimal place, 0.3, 0.9, something like that. We need to understand the concept of what an amphoteric substance is, that at equilibrium, water still kind of ionizes just a little bit, and that's an amphoteric substance. It can either act like a proton donor or act like a proton receiver, like a base or an acid, just depending on what it's mixed with. And then we can use that special equilibrium expression called the Kw, or the ion product constant, to be able to calculate ion concentrations, either hydroxide or hydrogen concentrations. And then we can classify solutions as acidic, basic, or neutral based upon the comparison of those two ions. So there you go. You've got some math that you got to do. I'm betting you got to rewind this one and watch it again. So I'll see you in class tomorrow.